So just imagine you're a Russian company, you're based in Moscow, where you're doing some financial business, and 100% of your business is made online. So maybe you don't know, but you're the perfect target for this kind of extortion attack. So briefly, the very simple and insecure architecture, where you've got the client, you've got the internet, well, big router indeed, which does some routing and some ACLs, very basic one, and some front-end servers and database in the back. So in terms of functional aspects of the front-end servers, well, what basically they do some user authentication. They get the request from the user and then format them and forward them to the DB servers. That's it. Technically speaking, the application is running on top of high TCP port, and all the traffic is encrypted with proprietary encryption. Okay. Also, something that's quite important is that this end user is very paranoid and doesn't provide any information about the application, the network, or whatever. So, the first wave. Well, on T0, well, some misbehavior were identified. So basically, the front-end server started to freeze. Also, it was not possible to establish any more connection to the server. And we also identified some very high usage, CPU usage on the routers. So we did some traces of the traffic. And we discovered something which is very classical. So it means we've got a single target on single port, and we've got thousands of different sources. And, well, all the packets were only SYNs. So this is typically a SYN flap. Well, like 30 minutes later, the IT manager was contacted via the ICQ, and, well, just had to pay for a certain amount of $1 million, else the attack would start again in 36 hours and would last forever. Well, this end user didn't give us any details about the amount and the way to, well, to give the money. But from my experience, there are two main ways. First one is just to pay a consulting company to get protection. The second one is, well, just to transfer the money. Each time it's consulting company or bank, which are in such countries that you cannot sue them. And, well, 60 minutes after the beginning of the attack, everything stopped, and that's it. So, first of all, what can you do against SYN flap? From the end user point of view, the best solution is to implement what we call the SYN cookies. So basically, it's just a trade-off between the TCB, well, the transmission control block, and CPU resources. So instead of generating random sequence numbers, the server is going to calculate them. So we don't have any more table. We're just going to calculate based, well, normally only on, well, some network parameters and time. But this way, it means that you can guess this sequence number. And we don't want our servers to become, well, to be spoofing ready. So you have to add like a random seed and generate the sequence number thanks to a one-way hash function. Okay, this way you're a little bit more secure. Also, you know that, okay, you don't have any more TCB, but you still have a lot of CPU usage because you have to do all these calculations. So if you set up the SYN cookies on the server and you get like 150,000 packets per second, you're sure that the server is going to die anyway. So you have to find a dedicated device that will perform this calculation for you. From the telco side, well, one of the best solutions today is to use the URPF mechanism. So, well, the strict mechanism is simply, well, you get packet and you see if the source address belongs to, well, the forwarding information base of the ingress interface. If it's not the case, you just drop the packet. So it's working pretty well for, you know, the end user edge, because here you've got just one link to the customer, and also you just know the IP address is there. So, well, it's pretty well working. But for telco interconnection, well, it doesn't work because packets can come from different interfaces according to the routing process. So, well, the only thing that you can do is to use what we call the lose mode. The lose mode is just to say, well, if the packet source address doesn't belong to any address, IP address or network in my routing table, so I drop it. So it clearly means that only packets coming from reserved address or RFC 1918 will be dropped. So it's not enough. A new mechanism now is to use what we call the virtual routing and forwarding, which is just to provide a routing table for each eBGP session. So this way we'll be able to do proper filtering. But also, you know, when you've got a SYN flood like this, well, this one was not so huge, but sometimes you have to handle SYN floods with like 2 gigs of SYNs. So here, in fact, the attack will not even reach the target because all those packets are going to kill all the device equipment of the telco all the way down to the target. So it means that we have to protect the infrastructure of the telco. So, well, basically what is done today is just doing what we call the black hole routing, which is to say I define an IP address on the routers, and this IP address is going to be routed to near zero, which is like kind of dev null. And well, then when I see there's an attack, I just issue a new BGP send packet just to announce a new route for this target to the IP address linked to node 0, and that's it. So, okay, from the attacker point of view, and even for the end user, it's like the DOS attack is successful because no packet can go anymore to the target, but we preserve the infrastructure of the telco. Okay, so we had 36 hours to protect this end user. Well, there were some issues anyway. First of all, black hole routing was not acceptable. Well, it's normal. This guy wanted this application to remain reachable from the internet. What's more, you cannot call a telco and just tell him, well, you have to set up something in 36 hours. You know that this kind of infrastructure cannot be changed so fast. So we had to, just say we're alone, and we analyzed a little bit what we got. First of all, we had spoofed sources. Okay, it was obvious, so we cannot set up ACL. Also, another issue is that, you know, this attack was a non-standard port, and there was no scanning before. So it means that the attacker knew the application. So, well, it's probable that it's got the client, the proprietary client, and also it's going to launch application layer attacks. So it was a major concern for us. So, in 36 hours, what could we do, and what did we? First of all, we provided a specific device just to provide SYN cookies protection. Okay, that's one. Also, we set up a stateful firewall behind the SYN cookie device. Because if you just set up the stateful firewall before all those SYNs are filtered, you're sure that the firewall is going to die because that's too much packet per second to analyze. And we had some limits. We were very afraid about the internet access router because 150,000 packets per second is hardly the limit you can handle. So, second wave. First, we had some layer level attack, network level attack. Well, it started with the same SYN flood that we had for the first wave. So we were not really afraid about that, except that we were interested in all the attack, mechanism because we were there when it started. And we saw that there were 3 steps. First of all, we had like 50K packets per second. Then 5 minutes later, it grew up to 100 and then 150. That was interesting for further analysis because we thought that there are multiple botnets involved in the attack. And all this has been successfully blocked, so we were quite happy with that. And 20 minutes, half an hour after the beginning of the second wave, we started to see new packets. So we had, an extra 50K packets first, but it was no more SYNs. It were, anomaly packets. So this is also a way to generate some denial of service attacks. These were like Christmas tree with this infamous push flag. We had some land attack and some SYNAC reflection, which usually damage your servers. And what was funny is that at first we had like 150K packets for just SYN flood and 50K packets for anomalies. And it changed to 100K and 100K, and then 100K for 50Ks for SYNs and 150 for anomalies. So we see that the bots have been reconfigured to change the attack and try to have it effective. And what can you do against this kind of attack? In order to detect what seems obvious is just to say, okay, I've got a set of signatures. I'm going to analyze each and every packet against these signatures. That's too much signatures, too much packet. You're going to kill your device, your IDS, IPS, or whatever. The second solution is that, well, just think about it. You know, this kind of attack rely on very high load of packets. So maybe you can just sample the traffic and maybe analyze and compare just one packet out of 100 or 1,000. So this works pretty well. Another way is just to do some heuristic analysis. So, but we couldn't do that here because we didn't have any baseline. Okay, we were under attack. So how to know which is normal traffic, abnormal traffic? So we had to rely on the second solution. In terms of blocking, you know, this kind of attack can be blocked with a stateful firewall. Because when you receive a SYNAC from a reflection attack, it's SYNAC not belonging to any session. It's going to be dropped. When you got a Christmas tree, that's the same. So, but the problem here, once again, is the performance of the firewall. Second one is to have a dedicated inline equipment. Well, we already had it, in fact, so we relied on this solution. There's another one, which is just to say, okay, all the offending traffic, traffic that looks suspicious, will be redirected to what we call washing machine. So it's pretty cool because the machine, well, this device just have to handle suspicious traffic. So there's a need for performance which is a little bit lower. However, here the end user didn't want us to touch the router or whatever. So, okay, we kept on working with this equipment we had in mind, and it worked pretty well. So, okay, we're quite happy. But, well, we're afraid to get some application layer attacks, and this is what we got. Well, what happened here? It's very simple. You know, sessions were completely established this time. It was not SYN cookies or SYN flood or this kind of attack. Just SYN, SYNAC, hack, and then send some garbage to the server. Okay, nothing to do with the application, but anyway. And what happened is that after like 5,000 sessions per second, well, the server would not accept any more connections. So I think we reached a kind of internal limit of the application. And there was no way to prevent this kind of attack except if you got more information about this application. Well, I told you, those guys were very paranoid, and the only thing they said is that in the first data packet, the payload will start with 0001. That's it. So the only solution was to set up a stateful rule that would say, okay, I get SYN, SYNAC, hack, and then a packet, and the first bytes of the TCP data will be 0001. Okay. It worked pretty well also. What was interesting also is that at this stage, the attacker had to reveal the IP addresses of its bots because it's through TCP sessions, so no more spoofing is possible. So we started to think about how we can maybe, sue the guy. But we don't have much time to think about that because, well, we started to have very weird kind of packets. Well, once again, session is established, and then we got these packets coming from the boats with, the TCP data starting with 0001, and then some garbage. And then the application crashed, well, since the first packet. So I guess it was kind of, buffer overflow in the application. But once again, customer didn't want us to have access to the system, or read the dumps, whatever. So when we asked maybe you can see developer, developer, he's not there. Well, he's there, but not really there. Maybe you can talk to him and blah, 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 blah. So, well, we couldn't do anything. So this is the reason why I call this a dirty blackmail story, because we couldn't protect the customer this time. But, well, first, let's go back to some analysis of the source. We identified like 4 botnets because of the steps in launching the attacks. These attacks are very basic. You can generate them with any tool like HPing, like Scapy, maybe it was a custom homemade bot, or we don't know. But what is sure is that the attacker knew how the application worked. So, at the very beginning, it was kind of smart not to get caught, just sending some attacks that, can be spoofed and very generic attacks. And then, I started to focus more and more on the application. And maybe that's why we were lucky. Because, in fact, I think that he was really afraid of getting caught, so he stopped the attack. Why did he stop the attack? Because, this end user didn't have so much customers, maybe 500, 1,000. So what we could do, as we had all the IP addresses of the bots, is just define ACLs with large range of IP addresses to be blacklisted. So it's very dirty, okay, but okay, we managed to block the attack. And as the attacker was I guess we're afraid of getting caught. He didn't try anymore. But if you had tried with another IP address, it would have worked once again. So, well, as a conclusion, what we can say is that, okay, security is a process, but you still need a brain. You can be paranoid at just, well, to a certain point. Now, if you don't want to trust anybody, just do the job by yourself. But here, in this situation, it was very, very hard for us to work for this guy. Don't want to give any information, but want us, to protect him. So that's it. If you've got any question? Yep.
The customer take additional steps to be more prepared for next time?
Sorry?
Does the customer take more steps to be better prepared for next time?
No. Well, it's a classical story in security, A guy says, well, I've got a problem. Wow, okay. So you come, you fix it, and that's it. Maybe you should try to build a security policy. Oh, that's okay, I'm safe. You know the story.
No, next time the attackers will be a little smarter.
Well, maybe, I don't know. I guess so. Okay. So thank you.